In the program, as you see, Marco Tavani is not Fiora Harrison, and he is going to talk about gamma ray astrophysics from space.
Yes, I will summarize a few ideas about quite exciting developments in gamma ray astrophysics. At the moment we have 2 missions operating, which is unusual. And in the past, of course, we had several very beautiful experiments. And of course, by gamma rays here, I mean photons able to produce pairs in your detector. So really, we are talking about 20, 30 MeV minimum energy going up. Okay. So about 15 years ago, we had ICRANet, a great experiment on the Gamma Ray Observatory. Now we have Agile, which is a small satellite, and Fermi working with silicon, so that it's extremely efficient compared to the past. And Agile is an Italian mission able to do both gamma ray detection simultaneously with the hard X-rays, which is an interesting twist. And Fermi, of course, is a bigger mission, which is also able to detect gamma rays in the tracker and also, for example, gamma ray bursts by hard X-ray instruments. So the gamma ray sky is full of interesting systems and surprises. And now we have the 3rd Fermi catalog with thousands of sources. Of course, we cannot talk about all of them. And now I will select a few topics here which are interesting for this conference. Okay. So I will focus especially on magnetized outflows, what we believe are magnetized outflows, and seeing evidence for the interplay between accretion and the jet formation. We have very beautiful microquasars in our galaxy. I will talk about that briefly, and which are connected, of course, with the much bigger systems where you have really gigantic monsters producing jets, like quasars or blazars. Then I will spend some time about what I'm calling super acceleration, which is a very interesting new phenomenon which we don't understand at the moment completely, but it's a very exciting way of accelerating particles which defies ideal MHD approximations and diffusive processes, which we see in the Crab Nebula. So the Crab Nebula is really now, again, at the center of attention. Then I will say a few words about some remarkable GRBs, just to set the stage for what happens next. I think the bottom line of what I'm saying is that we have now stronger evidence that shock or diffusive processes sometimes, or in several occasions, do not really explain very fast acceleration that we see in jets and in high energy phenomena. Okay, so this is a very general statement which possibly is connected with some other mechanism. Okay, and at the moment people are exploring, even though we are at the beginning of understanding, as Bruno Coppi just said. This could be a buzzword. It's not a buzzword, it's actually something that people are really trying hard, but it's a very difficult field, of course. And in general, therefore, the interplay between shocks and something else is now being reconsidered. Okay, so I will show some examples of that. Okay, for a few words about microquasars. Of course, they are exciting systems in our galaxy, where you have a companion star and either a black hole or neutron star. We are interested mostly in black hole systems, and these are, of course, the suspects. We had a list of objects well known before Agile and Fermi were launched, and we were expecting fireworks from all of them. And I still remember a very beautiful seminar that Remo gave in 1976 in the physics department here of this university, which I attended to, and convinced me that actually energy astrophysics is a very exciting thing. And he was talking about SS43. We don't have time to talk today about that, but it's, of course, a class of systems which are extremely interesting. So in gamma rays, only 2 systems are detected strongly. The others presumably are there, but are either very weak or very transient. We don't see them at the moment. Especially Cygnus X3 is the most active. But Agile, just because it has simultaneously also hard X-ray informations, was expecting to see many more, and we see only 2, and actually not in coincidence with the hard X-ray outbursts, like the nova that Neil Gerrels was talking about a few minutes ago, but with actually just the opposite behavior. Okay, so this is an interesting surprise. This is the Cygnus region. Cygnus X3 is a confused region. Cygnus X1 is a much cleaner region from the point of view of gamma ray background. And the first surprise was about Cygnus X3, okay, here. Okay, so this is the bat-like curve, a swift hard X-ray-like curve around 50 kV or so. And you see that when the curve has a minimum, and it happened in this particular time a few years ago 3 or 4 times, we see gamma ray flares. Just the opposite of what we expected. We expected some outburst of hard X-rays, presumably connected with the gamma ray emission. It's the other way around. Okay? But it is a repetitive pattern. So it's an extremely interesting thing. This was one of the flares in 2008. The source is monitored by Agile 14 times a day in hard X-rays. You see that it is at the minimum state in hard X-rays, then goes up. During this transition, which happens within a fraction of a day, we have a soft X-ray flare. We have a gamma ray significant, even though it's only 1 beam, but actually just for binning purposes. And then 1 day later, you see a Jansky radio flare of presumably a gigantic radioplasmoid being ejected from Cygnus X3. Okay, so this sequence is very interesting. Okay, so this transition is really the crucial point. Okay, so then we could make sense of this kind of idea that Cygnus X3 is living most of its time in this corona kind of system where hard X-rays are Comptonized and the corona is energized by the disk. So energy is pumped from the disk into the corona. It's not easy to sustain the corona. The corona has to be kept there. Okay? But occasionally, the corona disappears, the hard X-rays become soft X-rays. You can expose the system for a while, and then something happens. Okay, so the system becomes soft, and something happens. So what we believe it happens is that in this particular situation, the system stores energy, accumulates energy, and then at some point ejects the jet. And Cygnus X3 has done this many times. We have at least 5 or 6 episodes, okay, of this sort. It's very exciting. With the spectrum, with the gamma ray spectrum, which now is detected, which is presumably produced by the jet. Okay, so of course you can talk about leptonic, hadronic models. I don't have time now to go into that, but this is just to say that if we had a better detection, especially in the MeV range, 100 MeV range, we would really also address this very important question about protonic or leptonic compositions. SS433 we know has a lot of protons, has a lot of hadrons in the jet, but we don't know about these other guys. But this is a very important point about, of course, physics and energetics. A few words about Cygnus X1 that we looked very intensively with Fermi and Agile. Cygnus X1 is known to have these 2 states, the so-called hard, which presumably is quenched above just a few MeV, and then it has a very interesting soft state, which had some hope to see a tail, and therefore to detect gamma rays coming from this tail. Okay, so this was a very beautiful hope that we had, and both Fermi and Agile do not detect Cygnus X1 in the soft state, or even in the hard, on the average. There is an upper limit that is interesting, of course, from the point of view of modeling, but unfortunately it's not really what we were hoping for. But we know that Cygnus X1 is very active sometimes on very short time scales, both in the radio, definitely, transient radio events, but also sometimes in TV. This is at least one detection by MAGIC that if it is confirmed, it could be very exciting. So looking at the Agile data, we have a very beautiful and significant event at some point. I forgot when exactly it happened. I think in 2008, something like that, 2009. And then we had another event in the soft state, which again lasted 1 or 2 days. This particular last event is interesting because it happened exactly at the transition between the hard and soft. So again, you see, a black hole system has this transition, very sharp transition states, and during this moment, accelerate particles, and therefore you produce visible gamma rays. This has to be confirmed. This pattern, Cygnus X1 is a difficult cookie, but it's very exciting. Okay, and again, this is what we can see about the magnetization, the Comptonized spectrum here, and if there is indeed another extra component coming from the jet, this is the level. Okay, so it's something definitely for the future. But this connects me now with other systems. Paolo Giommi will talk about this on Saturday, about AGNs and blazars, therefore jets really produced by billion of solar masses black holes. This is a very famous object that we called actually Crazy Diamond. We gave it this name because it was very active since the very beginning of the Agile Emission, 2008, and then it's been active for 3-4 years. Very, very beautiful system that occasionally, of course, produces plasmoids. Okay, so this is a plasmoid, radioplasmoid ejected in late 2010, of course, detected a few months later, okay, in the radio. Okay, and this event here, if you trace it back, the late 2010 could be connected with this gigantic gamma ray episode, where really you have a gigantic jump in gamma rays, and this is so far the brightest gamma ray source in the sky, except for the sun, because the sun also had a very big flare a few years ago. But if you eliminate the sun, this is really definitely the brightest gamma ray source ever detected. And it has an interesting situation. You see, it has that before and during the flare, the optical and the X-rays vary, but not by a big amount, by maybe a factor of 2 or less, or something. The gamma rays vary by 1 order of magnitude, if not more. Okay, so this is what, in any case, this is known to have a Compton peak here in gamma ray energies, quite significant compared to the synchrotron peak. But during the flare, this kind of ratio between this peak and this peak is even increased. You see, this is even more extreme Compton dominance. It's very difficult to produce gamma rays without any optical or X-ray response, which is simultaneous in the canonical model. What is the canonical model? You have a jet, you have an inner region, not very inner, but something at the level of maybe 0.1 parsecs or so, the so-called broad light region, and there you expect synchrotron emission and inverse Compton emission, producing the 2 peaks, going more or less simultaneously. But this is not true anymore. Okay, so now we have evidence that several blazars show a drastic Compton dominance, and then also, of course, other effects that I don't have time to talk now that really show that maybe the emission site is not in this region, but is further out. Of course, when you move further out, you need to transfer energy there, and the things are maybe thinner, but you have more problems. Okay, so you really have to have enough soft photons, enough mechanisms, and enough acceleration that has to be ongoing at larger distances from the black hole. So in one way it's easier, in some other way it's more difficult. Okay. And of course, there are several ideas that people have been discussed about this. But really, this is what now it's coming out as one of the most interesting results of Fermi, especially Fermi, which has thousands of blazars and a few undulate detections, that we need to transport energy out from the jet. Okay? And either instabilities or something else has to keep the particle energized and has to provide the right conditions to produce the gamma rays. This is very dramatic. Just yesterday or 2 days ago, there was a paper on AstroPH on this very beautiful gamma ray flare by 3C279, which is an old friend among the blazars, and you see the gamma ray curve, which is very spiky. By the way, this level is almost the level of 3C454. It's smaller, but it's very high. And you see that at some point, a photon with an energy of 52 GeV was detected. Definitely, this photon cannot come from the Broadway region, it has to come from the outside. Okay? So this is very beautiful confirmation that transport of energy from the black hole out has to be very efficient and has to be done by something. Yeah. And presumably magnetized outflows are what people should consider. And of course, the Crab Nebula is the queen of magnetized outflows. Okay, so everything there is in the nebula is magnetized, and of course you have seen the movie that I don't show about the little flickering of the inner part of the nebula that is of course energized by a very powerful pulsar, and you see this ring, inner ring, the torus in the X-rays, and the so-called southeast jet. So you have in the system the injection of more than 10 to the 40th electron positrons per second, and you model the spectrum, you see, from synchrotron emission and then inverse Compton emission with this kind of interesting physical models. But what is important at the steady state emission of the nebula, now I'm subtracting the contribution from the pulsar, of course, just the nebula in the Crab has the very distinct cutoff in the spectrum. You see around a few tenths of MeV up to hundreds of MeV, the spectrum really precipitously goes down, and this is interpreted as coming from the maximum energy that you can get from an acceleration and of course subject to cooling, where the acceleration is done with very simple but effective ideal concept of using an electric field which is equal to the magnetic field, and therefore you can use this kind of cyclotron frequency divided by gamma for the acceleration rate. Okay, this is a standard thing. It could be wrong, but it could be wrong by some factor alpha, which is less than unity, for example. Okay, so this is a sort of usual thing in an ideal MHD that makes sense as a starting point. Okay. The beautiful thing is that this model predicts that the photon energy, the synchrotron photon energy, has to reach a sort of maximum and is independent from the magnetic field. The maximum is independent of the field. Okay, so this is indeed confirmed by the synchrotron burn-off. That maximum corresponds exactly to what you see in the steady state. Why am I saying this? Why am I insisting so much? Is this true? Of course, it's not the end of the story. Okay. Because in 2010, the Crab had a gigantic violation of this simple modeling. And since then, actually, people have been detecting many gamma ray flares from the Crab. And here they are, Fermi and Undulate. This is one of the, so far, the brightest in April 2011. Okay, so definitely the Crab violates the synchrotron burn-off, and therefore ideal MHD, and therefore whatever is behind these concepts. Okay, so the flares are very fast, a few hours. and they are very efficient. Okay, so you have this kind of total energies and luminosities involved. So a substantial fraction of the spin-down luminosity from the pulsar is involved in these flares. And at the peaks, this is the brightest event, you can have a spectrum defined very, very nicely. This is a very beautiful detection by Fermi. Okay, so the spectrum, therefore, is here. You see, this is the normal state of the nebula, but then you have this component sticking out very dramatically. Okay? Can be modeled either as a quasi-monoenergetic relativistic Maxwellian, like a sort of distribution function of particles which is almost a delta function. Very unusual, but try that. Then you explain the data very well. If it's not a delta function, of course, it's a power lawish kind of distribution, then you expect to see some sort of tail. Okay? And the power law, of course, can extend wherever you want. But in any case, you see the contradiction with the simple model is in terms of this ratio of electric field over magnetic field, which, of course, ideal MHD predicts to be strictly less than unity, and here is actually larger than unity. So definitely ideal MHD is not working here. Okay? So it's not definite, and this is what I'm calling superacceleration. So the idea is whether you have a behavior with a power law connecting gamma rays with the X-rays and optical, or not. Okay? So you have something very confined that evolves in time. So the connection between gamma rays and optical and X-rays is much looser, and therefore it's much more difficult to understand what's going on. So people have been trying very hard, and if you zoom in, there are several candidates. Okay, there are these wisps, which could be a manifestation of instabilities of the outflow, where you can have particle acceleration. You have the so-called knot 1, which is very close to the pulsar. You have the so-called anvil region, which is sort of a starting point of the southeast jet, which extends here to the left. Okay, but you see, this is a very dramatic representation of a violation of ideal MHD. Okay, so that you would expect to connect gamma rays and X-rays and optical, and actually now we have that we know today that there is no direct connection. We tried, and we did not see any X-ray flaring or optical flaring simultaneously with the optical. So the truth has to be between this curve and this other curve. Okay, so you see the real flux has to go in between these two. So the approximation of a delta function is reasonable. Therefore, it's extreme, but it's reasonable. Okay, so therefore you have these properties, and you need a very strong parallel electric field. Okay, so that's the bottom line. Okay, so you need something which violates diffusive processes. It's not ideal MHD. It's something else. What is it? Well, some people call it magnetic reconnection. Some other people call it in some other way. But definitely, you need a very strong field which has to accelerate particles, and the particle cannot radiate in situ where it is accelerated, but it has to radiate somewhere later. Okay. So I don't have time to talk about all the different interesting possibilities. One interesting site is this anvil region, the so-called anvil region. You see, this is the pulsar, and this is the optical image of the anvil, which is a sort of ring-like beautiful structure. You see that? And these rings is something that you see also in the magnetized outflows. So this is a laboratory little experiment where you see these instabilities that the plasma physicists call kink instabilities. You see these kind of structures are formed sometimes by this instability. So it could be that the crab is actually living in one of these unstable modes. This is, by the way, time variable region. Okay, so we tried also as a first attempt to model the outflow, the southeast jet from the crab, using some reasonable parameters, and we wanted to see whether the observations here can be reproduced. And this is a magnetized outflow, of course, which can be studied in many ways, especially where it kinks. Okay, so this is an interesting first attempt, and you see that you don't know how to interpret these things, but these are regions in the magnetized outflows where the magnetic field is enhanced and the not the longitudinal, but the azimuthal component of the magnetic field, can also have opposite polarities, and therefore can form magnetic islands, which in principle can reconnect. Okay, so there's a very exciting possibility that, of course, has to be studied in much more detail, but this is exactly what we want. If these two islands have opposite polarities, then you can accelerate particles, and you can produce some interesting situation of acceleration along the flow without a shock, okay? Or without diffusive processes. Okay, this is what we are trying to do, and of course, it's not simple, but one important constraint is also radiation reaction along the direction of motion of the particle, not just the radiation reaction by synchrotron along the sort of perpendicular momentum component, but just along the p parallel, okay, which is, of course, has to be taken into account properly, and presumably the maximum energy that we see in the crab is dictated by this radiation reaction effect. So we see a sort of almost monochromatic distribution of particles, and this is what I'm calling super acceleration. So it defies the synchrotron Barnoff, it needs a E parallel, has a electric field larger than magnetic field by a factor of 3, the maximum energy is set by radiation reaction, and therefore produces a quasi delta function distributions. Okay. Is it magnetic field reconnection? Well, we don't know for sure, but it smells, many of these ingredients smell like reconnection, even though, of course, to do an exact calculation is difficult. I don't have time to talk about models, but this is definitely very active field at the moment. Numerical simulations at the moment cannot really duplicate cannot have a dynamic range of a Lorentz factor going to 10 to the 9th. Okay, so we go to 10 to the 2, maybe 10 to the 3 at maximum at the moment. But okay, they are starting to see situations where either magnetic islands or situations where the magnetic field can be non-trivial and accelerate particles. So gamma of 10 to the 3 already is interesting for blazars. Okay, so jets in blazars require a gamma of 10 to the 3, so it's at least for blazars interesting. The crab, of course, is beyond that, it's 10 to the 9. Okay, but we are, just working on that, and many groups are doing it. So this is a very exciting field. I think this is maybe one of the most exciting fields in high-energy theoretical astrophysics at the moment, is to understand what's going on here. Let me just conclude a few minutes on some gamma ray bursts. Gamma ray bursts are, of course, detected in gamma rays. A fraction of them is significantly detected. And we have, of course, the heritage by the previous generation, by ICRANet, that is important. Why am I saying this? Because we had a lot of expectations from ICRANet. And especially ICRANet has these interesting events of hard X-rays, very spiky. In this case, I think this is the Super Bowl, the so-called Super Bowl events. I don't know if the gamma ray burst people maybe will remember this terminology. This happened, I think, during the Super Bowl game in 1993, and lasting 200 milliseconds. And you see, these are the individual gamma rays seen by ICRANet. We said, but ICRANet has a dead time about 100 milliseconds. So if ICRANet could have a much smaller instrumental dead time, could have detected many more gamma rays here. This was our presumption. And the same, of course, happened also in other bursts. This one, it was the first one which shows this delayed gamma ray emission. Okay, so this is sort of afterglow, gamma ray afterglow. At that time was not called that way. 1994. You see that the ICRANet detected these photons, then was occulted by the Earth, and then again gamma rays came from the same region. Okay, so this was really a very beautiful event. So we wanted to improve the dead time. So both Fermi and Agile worked very, very hard in trying to improve the dead time, because we wanted to see many gamma rays coming in the prompt phase. Okay. Also about the rate, we could extrapolate, just ICRANet detected all bright GRBs, which happen in the field of view. And so we are expecting naively for Agile and Fermi to have many detections per year. We sort of do have several detections per year, but not as many as we expected. Okay, so the gamma ray phenomenon is definitely there, but is not as common as we thought from the simple extrapolations 15 years ago. Okay, this is the first point. Okay. And this can be also represented by the fact that studying just as the Agile sample, but it could be done also for Fermi, we tend to see the gamma rays are produced in the high fluence events, of course, but less in numbers than what we expected. So let me just briefly mention something about these three events. Okay? Two are short, and one is interesting for the reasons connected with what I just said about the crab. So let's talk first about the 130427A, which was detected by both Fermi and Agile. This is the Fermi detection, and also the hard X-ray light curve. And you see that the gamma rays come exactly at the end of, almost at the end of the hard X-ray emission. Nicely detection also by Agile. Why is it important? This is very important because you see that if you look at the photon energies detected by Fermi in this case as a function of time, and some of the energies are very, very large and too large to be explained by the canonical ideal MHD model that I just mentioned before, that we know it fails in the case of the crab. So the crab phenomenon can have applications also for GRBs, and this is one of them. So it's a very exciting point. Okay, then Agile had a lot of thought about that time, so we really wanted to have a very beautiful detection of short bursts, and we got some, and this is, let me just show a couple of them. One, redshift 0.9 is a very famous one for many reasons. It's famous because it's beautiful, 200, 300 milliseconds, very fast in hard X-rays. Here it is. No gamma rays coming during those 300 milliseconds. So there is no question about that time. Now that time is done well. It's a perfect instrument. Both Fermi and Agile are very powerful in this time domain. So if there are no gamma rays, means that really the emission, the gamma ray emission is delayed. Okay? And indeed, you see that the gamma rays come after the first phase. Okay? And the spectrum is very interesting. During the interval 1, which is this hard X-ray phase, you see how the spectrum peaks around a few MeV, and then actually has a sort of exponential decay with no gamma rays. But the spectrum of phase number 2, which starts immediately here, you see the transition between one and the other, has a completely different spectrum. Okay? So we go from a thermal, quasi-thermal, to completely power law, non-thermal behavior. Okay? And this is done within a fraction of a few tenths of milliseconds, I think. Okay? So this is a very dramatic effect. So these are the physical parameters. This burst is very famous because it could be used also to set a limit on the possible violation of Lorentz invariance, because indeed the time scales are such that if you assume that the emission has a simple spectrum, which is of course an assumption, then from the GV gamma rays you can get a constraint on the possible violation of Lorentz invariance. So this was done by the Fermi team, which is very nice. So the second and last event I want to talk about is this one, again a short, very large redshift. So before Neil said the shorts usually are detected close, this one is an exception, is a short detected 2.4, the redshift 2.4. Crossing the field of view of Agile, you see, because Agile is spinning at the moment, and therefore it spins, the gamma ray burst just happens to have a sort of strip. very short, and this is the MEV light curve, and this is the gamma ray light curve, with the gamma rays coming, you see, after the first spike, which was just a few gamma rays, you have a lot of gamma rays coming tens or hundreds of seconds later. Okay? And this is the spectrum. Again, it's not as dramatic as the other one, but it has a similar shape. So that, again, quasi-thermal peak at around, in this case, a few hundreds of keV, and then definitely something non-thermal, extending to larger energies. Okay? So it would be nice to talk about theory, but I guess next talks will address that, so we will postpone the discussion about the interpretation of this later. But this is very beautiful and very dramatic. So conclusions, definitely we are entering into a regime where non-diffusive and very fast processes enter into the game. Therefore, we really have to reconsider acceleration from scratch in some way. Both nebular environments, which are by definition optically thin, so very clean environments with a lot of magnetized plasma, so that they really are very beautiful laboratories where you can study all these effects, and jets can possibly lead to ideas that the energy has to be transported out, has to be dissipated very fast, and therefore it smells like magnetic reconnection, even though, again, we have a long way to understand really how it works. Okay. And the crab phenomenon, of course, is not only for the pulsar people interest, but it's a very general kind of mechanism that now we see that as the tip of the iceberg in the crab, but it could be applied in many other systems. So this is really something that in the future, I think, will guide our investigations. So we need, of course, to go beyond that. So as I said, sensitivities, especially in the hundreds of MeV or even below, are crucial. So we are thinking about new ideas about how to do that. At the moment, there are two gamma ray concepts missions being considered, Gamma 400 and Astrogam. There could be others, but anyway, so I think that this lesson that we are learning of going deeper and using gamma rays as a probe for this extreme phenomena is going to be more and more important in the future. Thank you very much.
Thank you, Marco. There is any question? Yes, I see two questions.
Hi, Marco. Regarding the violation of the synchrotron limit, so that limit is
Violation of?
Violation of the synchrotron limit,
Yes.
the maximum energy. That limit is actually in the co-moving frame, which is the rest frame of the jet, if it is relatively moving. So in the GRB case, you mentioned that it is actually violating the Doppler boosted value. But for crab, I just didn't see anyone discuss the possibility of Doppler boost.
No, of
if
course,
you
yes.
introduce a little bit of boost, then there's no problem, right?
No, right. So this, it was one of my transparencies had delta as the Doppler boosting factor. Of course, it was considered from the very beginning. It is a possibility. In the case of the crab, you know that the jet, the southeast jet, the torus is stable. The southeast jet has a gamma of about maybe 2. So if there is a Doppler boosting, is a factor of 2. So we don't really see a strong. In the gamma ray burst case, it's completely different. But in the crab, we tried. It was the obvious thing, and it doesn't really work very well. And consider that also optical and X-ray emission don't show any brightening that you would expect if there is also some sort of remnant in the optical and the X-ray of the phenomenon boosted by the angle, by the geometry. So it could be an effect, but it's not very strong.
I have a comment here. Elizabeth
Oh yeah, hi.
Alpino. Hi. Yeah, I have a comment regarding particle acceleration within reconnection sites by the reconnection process. Actually, we do have a very good or a much better understanding of this process of acceleration within magnetic reconnection discontinuities that are magnetic discontinuities. And myself and Lazarian, we have proposed this first order Fermi process occurring within these reconnection sites where particles are confined in the magnetic discontinuity and undergo head-on collisions with the magnetic fluctuations. And this is an intrinsically three-dimensional process. It doesn't require the islands. Actually, islands are a two-dimensional process, and the islands become open loops in 3 dimensions, and the particles are confined in these loops within the magnetic discontinuity. So that essentially we have, just like in shocks, a first-order Fermi process occurring within the magnetic discontinuity. That is the discontinuity layer provided by magnetic reconnection. And also this has been, actually we demonstrate this by means of numerical simulation, 3-dimensional MAGD simulations with test particles, and this has been published in Physical Review Letters in 2012. And this is pretty general and could be applied to any environment, either in the surroundings of black holes or along the jet. And
Marco,
actually,
may I ask you to
just let me finish.
Wait a minute.
And along the jet.
Excuse me. Wait a minute. May I ask you to give a short answer? Okay, go ahead.
But just
Elizabeth,
let me finish.
if you allow me
And
to
along
talk,
the
I could
jet.
talk for hours about this. You're right. I didn't have time to summarize the
No,
theoretical
it's
model.
fine, but
It is just in very short. The challenge is this: delta functions and short time scales.
Sure, yeah,
Okay.
it's perfect.
So this is not easy to do.
The short
Okay.
time scale.
Excuse me. You
along
go.
the jet.
You talk with Marco later.
Yes.
Now we have the coffee break, and we start again.